All right, so let's look at a question about flush and reload. Consider the following RSA code below. This is the square modulo, etc. So, and then there is a portion in which we test the value of E sub I, whether it's 1 or not. And then if 1, we perform multiply and modulo. If not, we don't do the following, right? And because this is the secret value, so the existence of this path of execution kind of is a source of that side channel, and it leaks various secret through various side channels. Okay, so let's see the question. So suppose the attacker can trigger a page containing the code above to be shared with the victim. Okay, so the code here is shared with the victim. Suppose that the program counter address of each instruction is hexadecimal 0FFA7983 plus the line number times 4 bytes. So this is the line number. And suppose its instruction is 4 bytes. Now, obviously, this is a simplification because these are not instructions. These are statements and some of them function calls. But for the sake of simplicity for this problem, we assume that each of these is just a single instruction. Okay. If the attacker wants to use flush and reload attack, what addresses can the attacker supply to the flush instruction? So basically, what should be flush? So let's kind of like start with like what's the instruction address. So in this case, the first instruction will be 0F 0x 0FF A7983. Now, because this is hexadecimal and we want to work, let's take the last let's take the last two. Let me see. Let's actually calculate the offset first, right? So the first, let me see. Suppose the PC address of each instruction is this plus the line number, which is in this case 1 plus 4 bytes plus binary of 4. Okay. Base binary, right? And this, the second line will be plus binary of, no, sorry, decimal. Decimal 4 bytes, decimal 8 bytes, decimal 12 bytes, decimal 16 bytes, and then these two right here, decimal of 20 bytes, decimal of 24 bytes. Okay. And then the other ones is, we don't really care. All right, so let's perform the addition. So the difficulty here is just converting this into into hexadecimal. But for the first few is easy. So you can just add 4 plus 3. That will be 7, right? So it will be 0x0FF A7987. And then plus 8. So 3 plus 8, that will be 11. And 11 will be B. And then plus 12. Plus 12, 12 plus 3, that's 15. So 15 will be E. Okay. Now after 15, the next will be, so this will be the maximum for hexadecimal, so it will wrap around, and then this one increases to 9. So 799. But what is the last digit? So the last digit, so after we wrap around, it will be 0, 1, 2, 3, right? So it goes back to 3. So you can see we start wrapping around. So the next one, 4 over this one. So this will be 7. And just like this one, it's kind of wrap around. The last one will be B. Okay? All right, so we have all the instruction addresses. If the attacker wants to use flush and reload attacks, what should be flush? Okay, so what instructions should we evict from the cache? Okay. The most obvious one is the multiply. Okay, because the multiply only appears inside the if statement, meaning that the the fact that it is brought back into the cache, it has to be because of you know, like if it has been evicted from the cache and it's brought back into the cache, it must be because the if statement is true. Okay, so we cl flush address 0x 0FFA 7997 for the multiply. Now, if we have a more precise timing, which is kind of like somewhere in here, we evict, we flush the modulo, and then somewhere here we measure the modulo. We can also utilize that. So this require a more precise timing, but it's also possible. So 799B. Okay, that's it.